Alright, so the first problem we have on the relative velocity packet involves a fishing boat with a maximum speed of 3 meters per second relative to the water. So the velocity of the boat relative to the water is 3. The water is flowing relative to the shore at a speed of 2 meters per second. And we want to know the maximum speed the boat can obtain relative to the shore. So in that case, the boat's movement would have to be in the same direction as the river's movement. So we would simply take the boat's speed plus the river's speed, and we get 5 meters per second. To get the minimum speed, in that case, the boat would have to go in the opposite direction of the shore, and in that case, we would have one vector going 3 meters per second, and the other one would have to be the opposite, or 2 meters per second. And the minimum speed we can obtain is 1 meters per second. Notice it wouldn't matter if I put the -3 and the +2. We get -1, but remember the speed is what they're asking for, and that's the magnitude. We're trying to find the lowest speed. Alright, with number 27, we're looking at a powerboat heading northwest at 13 meters per second relative to the water across a river that's flowing due north at 5 meters per second. So we've got the river speed going north at 5, and we have the boat which is traveling due northwest, which is halfway between north and west at 13 meters per second. So we're just going to add these two vectors like we normally would. Each one is going to have an x component and a y component. The first vector only points in the y direction, so its x component is going to be 0. Its y component is a +5, since all of that is directed north. For the second vector, we have, if we call east 0 degrees, it goes 90 plus another 45. So we have 135 degrees. So our x component will be 13 cosine of 135, and our y component will be 13 sine of 135. And remember, we're going to total all of our x's and we're going to total all of our y's. 13 cosine of 135 is -9.2, as it should be, since all the x components are directed to the left. And then if we add 5 and 13 sine of 135, we should get 14.2, and that should be directed in the positive, since we have a positive y plus a positive y. To get the magnitude, remember, we want to take the x component squared plus the y component squared using the Pythagorean theorem, and we do that, we're going to get 16.9, or 17, for our resultant vector, its magnitude. And remember, to find the angle, remember our resultant vector was pointing left 9.2 and up 14.2. So if we want to find this angle, we're going to have to take our tangent of tangent of theta equals 14.2 over 9.2, and if we do our inverse tangent of that, we're going to get theta equal to 57 degrees. But it looks like that theta is directed from west, so we could either say 57 degrees north of west, or we could take 180 subtracted from that and say it's at 123 degrees. Right, for number 28, we're looking at an airplane flying due south at 175 kilometers per hour. There's a wind blowing 85 kilometers per hour to the east, relative to the ground. So we want to find the plane speed and direction relative to the ground. Again, we're just going to add these two vectors. This time we don't have any angles other than 90 degrees involved. So we're just going to use the Pythagorean theorem. Our resultant equals the square root of 175 squared plus 85 squared. And that's going to give us 190 kilometers per hour for our resultant vector. And then to find the angle, we're just going to take, we can use this angle here. We're going to take the inverse tangent of 175 over 85, and that's going to give us 64 degrees for that theta right there. But again, if we're looking at the angle from where it's directed, we know that these would kind of be alternate interior angles here. So this angle up here would also be 64 degrees, and we could say 64 degrees south of east, or if you want to take that off of 360, you could say 190 kilometers per hour at 296 degrees. Now for this problem, we have an airplane with a speed of 285 kilometers per hour relative to the air, and there's a wind blowing at 30 degrees north of east relative to the earth at 95 kilometers per hour. We want to know which way the plane should head to land at an airport due north. So we want the plane, in other words, we want the resultant to be due north. So we need to find what direction this plane needs to fly in order for that resultant to be due north. And I should draw, we want the resultant to be due north. So in other words, my plane's velocity, if you think about it, if it's drifting northeast, the plane's going to want to have to fly kind of northwest to compensate for that. So in other words, we want this vector, the air vector, plus the plane speed vector, which is 285 at some angle, to equal some magnitude due north, or at an angle of 90 degrees. So when we're adding those vectors together, we have our first vector that is 95 kilometers per hour at 30 degrees. We have our second vector that has a magnitude of 285 at some angle we don't know. And then we want those two to add to our resultant vector of, we don't know the magnitude, so we'll just call it V, at an angle of 90 degrees. So our x components for all of those things, we'd have just like normal 95 cosine of 30, which would be 82. We would have 285 cosine of theta, and those two have to equal our velocity times the cosine of 90. And then for our y direction, we have 95 sine of 30, which is 47.5. We would have our 285 times the sine of theta, and those two are going to add together to give me the v sine of 90, the y component of my resultant vector. So if I have basically two equations here, I know that these two add to this one, and these two y components add to my resultant y component. If I know for a fact that the cosine of 90 is 0, so I can actually just cross this whole thing out and make it 0. I know that the sine of 90 is 1, so this is v times 1 or v. So I know first of all that 82 plus 285 cosine theta is equal to 0. So if I move 82 to the other side, I get 285 cosine theta equals negative 82. Divide both sides by 285, and I get that theta equals the inverse cosine of negative 82 over 285. Just put that in your calculator, and you should get 107 degrees for theta. Now we know theta, so we should be able to solve the second equation. We have 47.5 plus 285 sine of theta, and that's going to equal my v. I know that theta is 107, so I just take 47.5 plus 285 times the sine of 107, and I'm going to get a velocity of 320 kilometers per hour. So my final answer would be 320 kilometers per hour directed at 107 degrees relative to east. Alright, so for number 68, we have an airplane. 68, we have an airplane flying 200 kilometers per hour relative to the air, and we want to know its velocity. For part A, if it faces a 50 kilometer per hour tailwind, so wind coming from its tail, we're just going to add those two and get 250 kilometers per hour. For part B, we have a headwind now that it's facing towards the airplane's head, so the two vectors are opposing each other. We're going to get 200 minus 50, or 150 kilometers per hour.